Okay, so we have 20 minutes. So probably it is bad idea to start early because many people may be interested in your talk and they have this schedule. So what I want to ask you the following. The thermalization of harmonic oscillator Unruh-Dewitt detectors was withdrew. So talk from 6:30 to 6:50 was withdrew. And I would like to ask the last speaker if he want to wait or just to do his talk at 6:30 or to wait until 6:50. So I am asking Sander Kalikar. He is not here. He is not here. Let me check how many people are here. Can you hear me?
I can.
Yeah, okay.
Yes, I can.
Yeah, he is not still here and probably he will come later. I think that the ideas should be circulating free between different areas of physics. And it is known, for example, that the first idea about Higgs boson was due to Anderson. This is famous Nobel Prize winner, famous condensed matter physicist, but he published it in a different magazines and so on. So there should be ideas. Because when I talk about the breakdown of the equivalence principle, I always get opinion that people don't know how hydrogen atoms works. And I have a difficulties, at least probably basic knowledge should be available for all physicists. Okay, so we have 5 minutes. You may probably start if you want. I mean, Ankit.
Okay, should I start then?
Yeah, you can have 5 minutes more.
Okay. That's fine
Okay.
with me.
Okay, so I'm going to share my screen now.
Yeah.
So can you see my screen?
No. Yes. Yes. I can.
Okay. Okay.
So I should make introduction. So this is talk of Ankit Hanuka. Do you spell your name Hanuka or Danuka?
Dhanuka.
Danuka.
Yeah.
And
Dhanuka.
Danuka.
this is Malawi, India, Department of Physics. And what is IISER, Mahali?
Yeah. It's the institute that I am affiliated with.
This is institute. So fine.
Yeah.
Yeah, you can start and have 5 minutes more.
Okay. Before I start my presentation, I would like to thank the organizers of the meeting to give me this wonderful opportunity to present my work. In this presentation, I'm going to discuss about the behavior of stress energy correlator in d theta spacetime as well as FRW spacetime. The results that I'm going to present, they are based on work which is given in this paper, which I have written with my PhD supervisor, Dr. Kinjak Lochan. The reason for studying stress energy correlator is to see whether quantum fluctuations, they are large or not. Because if quantum fluctuations are large, then first order semi-classical considerations, they are rendered incomplete, and one need to consider second order semi-classical methods to see whether the statements are robust or not. So the statement that I have just made, it will become more clear as I go along in my presentation. So yeah, the plan of my talk is that I will first talk about stochastic gravity, and in stochastic gravity, how does one quantify quantum fluctuations, and what is the effect of quantum fluctuations on the dynamics of classical geometry of the spacetime. Then I will talk about an equivalence that exists between quantum fields in de Sitter spacetime and quantum fields in FRW spacetime. And after that, I will discuss the behavior of noise kernel for quantum fields in de Sitter spacetime. Similarly, I will discuss about the behavior of noise kernel for quantum fields in FRW spacetimes. After having discussed these results, I will give what are the implications of these results. In classical GR, the dynamics of the classical geometry of the spacetime is given by Einstein's equation, where that is equation 1, where T mu nu is the energy momentum content of the space of the universe. Now this is the classical object, but if say one has quantum fields evolving in this space time, then how does one incorporate first quantum effects on the dynamics of the classical space time? That is done through what is called semi-classical Einstein equation, that is equation 2. And in equation 2, instead of using T mu nu, we use the expectation of T mu nu operator, that is the stress energy operator, with respect to some state in which the quantum field is supposed to be in, and then we solve this equation 2. Here the superscript R implies that this object should be properly regularized and renormalized before using it into this equation. This is as far as the first order quantum effects are concerned. Now, if one wants to consider second order quantum effects, that is the quantum fluctuations, then one can take many routes, but one route that I'm going to take is the paradigm of stochastic gravity. In stochastic gravity, quantum fluctuations, they are quantified by what is called noise kernel or stress energy correlator, which is defined as in equation 3. That is, it is the vacuum expectation of anti-commutator of small TAB and small TCD. And the small TAB, small TCD, they are nothing but stress energy operators subtracted by the expectation of stress energy operator with respect to vacuum state. Here one could have taken any state, but for the simplicity of the calculations, I am going to take it to be a very specific state, the vacuum state. And okay, now we have been able to quantify quantum fluctuations through noise kernel. Now the natural question that one asks is how these quantum fluctuations they affect the dynamics of the classical geometry of the spacetime. This is given by what is called Einstein-Langevin equation, that is equation 4. And in equation 4, all the quantities, they have their usual meaning, except that instead of evaluating them for classical background that we started out with, now we calculate them for classical background plus metric perturbations, which are given by H. And there are two extra tensors in it, that is capital A, capital B, which one gets when one considers the metric variation of the Einstein-Hilbert action with the term like R square as well as square of the wild tensor. And these constants alpha and beta, they are constants like lambda and g, which are to be determined experimentally. Now, however, the most important quantity in this equation is this xi AB, which is a stochastic term, and this is the term which is related to the noise kernel, and it is related to the noise kernel by this equation, where this expectation is not a quantum expectation but a ensemble averaging. And once we have now, since we have seen that noise kernel, it plays an important role in determining the effect of quantum fluctuations on the classical geometry in this paradigm of stochastic gravity, it is interesting to see the behavior of noise kernel for cosmologically interesting spacetimes, that is de Sitter spacetime and FRW spacetimes. So before I go to that, I will give an equivalence that exists between quantum fields in de Sitter spacetime and quantum fields in FRW spacetime, because that will be helpful when we'll consider the behavior of noise kernel in FRW spacetime, and that we can relate to behavior of noise kernel in de Sitter spacetime. So the idea is that we consider a massless scalar field in power law FRW spacetime, that is spacetime with A of eta is equal to h eta to the power minus q, and we know that its section is given by 5. And now what do? We express this massless scalar field as this h eta to the power q minus 1 times some field psi of x, and we substitute this into equation 5. And after having substituted it into equation 5, we find that equation 5, the expression 5, it transforms to equation 6, which is nothing but the action for a scalar field, massive scalar field in a spacetime with scaling factor b of eta. Now, if we demand that the scale factor b of eta is equal to 1 by h eta, that is, it is that of de Sitter spacetime, then this m square gets related to the exponent of the scaling factor in the starting FRW spacetime through this relation. So what we have basically been able to achieve is to relate a massless scalar field in FRW spacetime to a massive scalar field in de Sitter spacetime, where the mass is related to the exponent of the scaling factor of the de Sitter spacetime. And I have reproduced this expression here, 7. And from this expression, we see that when mass lies between this range 0 to 3 by 2, I will explain the reason that why I am taking m by h to lie between this range. Then q lies between -2 to 1. I will be interested in looking at the behavior of noise kernel for late time universe. And by late time universe, I mean the limit of eta for which a of eta goes to infinity. And for negative values of q, for eta going to infinity, a of eta goes to infinity, therefore it is the late time universe limit. Whereas for positive values of q, eta going to 0 corresponds to the late time universe limit. And since we know that in quantum field theory, in covered spacetime, the most important object is the Weightman function. Therefore, I am also giving the relation that exists between the quantum fields in the two spacetime.
That sounds good.
That is the Weightman function for a massless scalar field in FRW spacetime is h eta to the power q minus 1, h eta prime to the power q minus 1 times Weightman function for a massless for a massive scalar field, associated massive scalar
Yes,
field.
I can turn the sound off.
Now,
I mean, when I'm in the room listening to the meetings.
Oh, yes, I see. Very clever.
And then I'll.
So it started then.
Yeah, it's very. I mean, it's 9:30, so.
Yes.
So please ask
Can you
questions
tell if it's
at the end of the talk. Yeah.
Weightman, you didn't give a topic. It's relation between Weightman functions.
Please ask
What?
questions
This
at the
relation
end
8?
of the talk.
Oh, mute.
Yes, this relation is obtained from the relation between phi of x and psi of x given here, the transformation that I considered.
Yeah, all
And if I
questions
substitute
at
it
the
into
end. So please.
should I continue my talk?
Yeah, you should continue your talk.
Okay, so now we have given this after having related this massless scalar field in FRW spacetime to a massive scalar field in de Sitter spacetime. We can calculate the behavior of noise kernel, but since we can calculate it for any state, but I will be calculating it for a particular state, that is the Bunch-Davies state. And the Bunch-Davies state, the Weightman function is given by equation 9, and that is the Weightman function is proportional to 2f1 function, where a and b are related to mass through this relation, and z is the invariant distance between 2 points on the de Sitter spacetime, and its expression is given by this. And so, okay, so now we know that the stress energy operator one obtains by considering the metric variation of the matter action, and if we do that, we can write stress energy operator as in equation 10. Now I'm going to use a little trick in order to make the calculation easier, and that little trick is point splitting technique, in which we write the stress energy operator as a differential operator PAB acting on a product of fields at point x and y, and then we take the limit y going to x, and then that gives us the stress energy operator. And the expression for PAB of xy is this given in expression 12. Now what do? We substitute this expression of stress energy operator into the vacuum expectation of TAB and TCD considered at two different spatial points. And after using Wick's theorem, one can show that this thing becomes TAB, TCD acting on Whiteman functions at xx prime, yy prime, and finally, after evaluating this, we will have to take the limit y going to x and y prime going to x prime. But the expression corresponding to this is a bit involved and very long. Therefore, I haven't reproduced it, but it is that expression which I am going to use to quote the results for the behavior of the stress energy for this noise kernel. And also related to the noise kernel is another correlator, that is the energy density correlator. So how do we so one can define energy density at any space-time point x by considering observers which have fixed values of static spatial coordinates. And for that we can then consider the tangent fields, and the tangent field will be like 1 0 0 0. And if we contract the stress energy operator with these tangent field, then we get energy density at point x, and then one can calculate the correlator of energy density at point x and energy density at point y, and that can then be related to the noise kernel through equation 14. So equation 14 gives the energy density correlator, and it is noise kernel divided by A of eta times A of eta prime whole square. And I will give the results for the behavior of noise kernel for a specific case when eta is equal to eta prime, that is on constant time sheets, but with fixed spatial non-zero distance, that is delta x is equal to 0. Yeah. So what we find through the relation that I gave earlier, that is this relation 13, if we substitute the expression of Bunch-Davies vacuum in that, we find that the noise kernel, it behaves like eta to the power 2 minus 4 nu in eta going to 0 limit, because for this eta spacetime eta going to 0 limit, it corresponds to the A of eta going to 0, A of eta going to infinity. And here nu is this under root 9 by 4 minus m square by h square. And what we find from this expression 15 is that noise kernel shows a sort of phase transition, that is the noise kernel is 0 when nu is changed from 0 to half. At half it attains this value, this thing, that is it is inversely proportional to delta x to the power 4, but after nu gets higher than half, it diverges. So in that sense there is this rough analogy with the phase transition, and from this behavior of noise kernel, one can calculate the behavior for energy density correlator in the same limit, and one finds that for nu lying between 0 to 3 by 2, the energy density correlator is 0, but for nu equal to 3 by 2, it becomes a constant. And this is as far as the behavior of noise kernel for quantum fields in d-theta spacetime is concerned. Now one can also look at the behavior of noise kernel for quantum fields in FRW spacetimes. Since I earlier gave the relation between Whiteman function for a massless scalar field in FRW spacetime in terms of Whiteman function for corresponding massive scalar field in d-theta spacetime, using that relation, and one can express the noise kernel for FRW spacetime in terms of the noise kernel of quantum fields in d-theta spacetime, and from that one sees that the noise kernel for positive values of q in the eta going to 0 limit, it remains constant. And here, since I earlier also said that for positive values of q, it is the eta going to 0 limit that corresponds to the scaling factor going to infinity. Therefore, I am considering eta going to 0 limit here. And for negative values of q, it is the eta going to infinity limit that corresponds to the A of eta going to infinity limit. And for that, the noise kernel behaves, the noise kernel goes to 0. And the corresponding energy density correlator, it's vanishing in both the cases. And yeah. Now the above behavior that we have seen for different values of Q for of FRW spacetimes, it can also be related to the equation of state parameter omega, and through the relation Q equal to -2/1 plus 3 omega. And what we find is that for omega lying between 0 to infinity, the noise kernel, it is 0. For omega lying between -infinity to -1, the noise kernel is constant. Whereas for omega lying between 0 to -1, the noise kernel is divergent. That corresponds to this yellow strip. However, the values of Q's that I've considered, that is from -2 to 1, it corresponds to the red strip and this green strip only. And I consider that limit because I wanted to make sure that this nu is always real. But if I allow for this nu to also take imaginary value, then one can have a value of omega corresponding between 0 to -1 as well, which corresponds to this yellow strip. And so now I will summarize the results. So we have observed that in de Sitter case, the noise kernel undergoes some sort of phase transition, that is from no correction to infinite stochastic correction, as nu is changed from 0 to 3/2. In the case of FRW spacetimes, for negative values of Q, there are no stochastic corrections. For example, in the radiation dominated case, that corresponds to Q equal to -1. There are no stochastic corrections. While for positive Q values, there are finite stochastic corrections. However, for pressureless thrust-driven universe, that is Q corresponding to -2, the noise kernel blows up for late time. So the reason for doing all of this was to see whether the quantum fluctuations, they are large or not. And we have seen that in some cases the quantum fluctuations are large. And therefore the take home message is that in certain cases where the quantum fluctuations are large, one cannot rely upon first order semi-classical consideration. One need to perform second order semi-classical calculations to ascertain whether the first order results, they hold true or not. And only then one can make more conclusive and robust statements. Yeah, that is all. Thank you.
Now the talk is open for questions.
Yes, I have a question. Yes,
Yes,
sir.
yes.
I thought your treatment of the noise kernel was very revealing, and I want to thank you for that. Could you please go to slide 7? It's not a criticism, it's just a general question which I have about what you had on slide 7.
Okay.
All right. No, I think it's that's slide 7. I think it's the one. It's a go to the next slide. I think next slide.
This slide?
All right. You have this very,
This slide?
yeah, right over here. You have this very, very precise treatment of this N, or we're going to late time universe, and the late time universe and this Q, this open type of, this Q is very closely is bound, and that's for M of H right over here. This is what you were doing, and you're doing with respect to this type of a relation. And what I'm saying is I'm going to ask a very naive question about equation 7. Is this in any way related towards some of the dynamics when you went to the so-called the noise kernel? Remember how you defined the noise kernel? Noise kernel.
Yeah. No, yeah. So this relation 7, what do you want to ask about it?
Yeah, what I'm asking is there a relationship between equation 7 and what you're doing when you have your description of the noise kernel?
No. So here equation 7, it gives, so here what I have shown is that a massless scalar field in a power law FRW spacetime, it can be related to a massive scalar field in de Sitter spacetime, where the mass is related to the exponent of the scaling factor. So and so this holds true even if we are not calculating noise kernel, but I say if one wants to calculate noise kernel for massless scalar field in FRW spacetime, then using this relation 8, one can express the noise kernel for massless scalar field in FRW spacetime in terms of noise kernel for massive scalar field in d theta spacetime, where mass is given by equation 7.
Thank you. Thank you very much
Yeah.
for your kind elucidation for an old man. Thank you very much. I'm in your debt.
Okay,
Thank you.
more questions. Maybe we have a time. I would like to comment this semi-classical Einstein equation. Could you show me first or second? I don't remember where.
Yeah, this
It's,
equation
yeah,
second.
semi-classical. So you should, of course, the work is fine and very good, but you should be careful about this equation. This is not quantum gravity. And for example, it is known that if you have two big masses and you have a quantum superposition of particle to be to have mass 1 or to have mass 2, then this equation is valid because the wave functions is collapsed and it works only for M1 or M2. So just my comment is that is not true quantum gravitation, but work is very important. Yeah.
Okay. Okay. So this equation 2 is not it's not an equation of quantum gravity. It assumes that the background is classical.
Yeah. Yeah.
Yeah.
But also this is a little bit suspicious term when you have two masses, for example, and when you have superposition of a particle to be in two levels, then you have a problem here. You have expectation value, but experiment shows that there is no interference term, that the real gravitational field choose only one mass from here. Okay, this is just because we have too much time. This is not your fault. Many people consider this equation, and people don't have something more suitable than this equation.
I have one kind of subsidiary question which adds on what you brought up, and that there was a question called so-called, could any of this type of formulation lead to the action at a distance, so to speak, in terms of if they corrected the problem that you mentioned about, it's not really a quantum field, but could what has been presented be relevant to the action at a distance problem?
Action at a distance, you mean instantaneous reaction. So as far as the matter thing is concerned, that is being treated as quantum. So for the and since even at the classical GR level, the special relativity is encoded in it, at least locally. So I don't think the action at a distance thing will hold true, because that is true only in Newtonian framework.
Thank you, sir.
Ankit, thank you very much.
Yes, yes.
So
Okay.
the next,
thank you, sir.
yeah, thank you for a wonderful talk. The next speaker is Dr. Yuki Yokakura Riken from Japan. And the title, Interior of Typical Black Holes.
Or can you see my slide?
Yes.
Okay, just a moment.
Now full screen. Yeah.
Yeah,
More.
and you have you see my pointer?
Yes, I see.
Okay. Yes. Can I start? Okay. So, thank you very much for the introduction. Hi, I'm Yukio Kokura from Riken in Japan. In my talk, we will consider what is black hole in quantum theory. To do that, we will analyze time evolution of spherical collapsing matter, including our particle creation during the collapse. As you know, in such a time-dependent geometry, particle creation occurs generically. So, in order to consider a precise time evolution of gravitational system, we need include back reaction from the particle creation. To do that, from now we will solve semi-classical Einstein equation coupled with and massless free scalar fields. And after solving this equation system, after getting some solution, then we want to see what is formed and horizon is formed or not. So this, and depending on the result, we want to see what the black hole is in quantum theory. This is a plan. Before giving our main result, first, I like explain our basic idea, okay? So first, we have our spherical collapsing matter, this one, and we can regard it as many spherical shells. These blue lines, okay? These are shells. Now, we focus on one shell, this one. So then, the shell is coming like this. Then the geometry is changing in time, of course. As I said, particle creation can occur. This particle creation released the energy of the system. So the short suit radius of the system A decreases like this in time. From now, we want to see by solving this time evolution system where we want to see where the shell is going. Okay, let's consider it. To do that, we support at this stage, the system evaporates like a black hole. This means this particle creation is like our usual Hawking radiation. So here, this region is changing in time, and of course, this region is not the vacuum region. To express this time-dependent geometry, we use this simple candidate metric, just a candidate. So here, A is decreases according to the Stefan-Boltzmann law of Hawking temperature. So this sigma means intensity of the Hawking radiation. It is just order 1 constant and proportional to h bar, g, and n. N is degrees of freedom of matter fields in the Lagrangian. Now, in this time-dependent geometry, when the shell, the position Rs, the shell is coming here near the short suit radius, then the shell behaves ultra-relativistic. So the equation motion is given by this simple one. By solving this equation motion, we can see where the shell is going. Okay, let's solve it. Let's focus on the difference delta R, this one, the difference between the shell and the short suit radius. Of course, this delta R is much smaller than the A itself. So we can approximate like this. Here, we replace Rs by A like this. Then the equation motion becomes this simple one. Okay, please look at the first term, blue one. This blue one is negative. this expresses the effect of the props. On the other hand, this violet one, the second one, is positive because of this box equation, evaporation. The point is, these two terms are balanced when the delta R becomes order of 1 over A. So the right-hand side vanishes. We have delta R is approaching this value. This means the shell behaves asymptotically like this. The point is, this second term has the proper length or order of root n Planck length. So if we have many matter fields, then this second term is meaningful in the semi-classical description. In this way, the shell cannot enter the time-dependent geometry. Rather, the shell is just approaches this position. Okay, let's go back to our basic idea. If each shell evaporates by particle creation like this, then the shell approaches here. Therefore, we can imagine all the shells just shrink and pile up, then this dense object is formed. The matter, that is, the shells and the Hawking radiation, are filled inside this position. Here, A means the total shortest radius. This position is just a boundary between the dense region and exterior dilute region. In this sense, we call it just the surface of the object. In this way, if we include back reaction of the particle creation during the collapsing process, then no horizon is formed. Rather, some dense object is formed. We can see this object should be the black hole in quantum theory. This is our basic idea. However, we have a question. Can this idea be realized as a solution of a semi-classical Einstein equation? What are the metric and the state? Okay. To answer these questions, we will do a self-consistent argument, this one. Let's start it. In step 1, we construct a candidate metric. Motivated by the basic idea, we model a spherical plasma matter as many nutshells, and we obtain the following metric, this one. The black one expresses this exterior region. On the other hand, this blue one represents interior dense region. These two metrics are connected at the null surface here, and we can check these two metrics are satisfied Israel's junction condition indeed. And this blue one depends on two parameters. One is intensity sigma, and the other is a ratio eta. This ratio is between radial pressure and energy density. These two parameters will be fixed by solving semi-classical Einstein equation later, okay? So interesting point is, this blue one, interior metric, is locally ADS 2 times S2 with ADS radius, order of root n Planck length. Anyway, this is our candidate metric. Okay, let's go, step 2. We find a candidate state psi. Before that, we study field equation, a triangle equation for each mode in the background geometry. Our background geometry is this one, okay? As you know, in the WKB approximation, the region with non-negative momentum square corresponds to the classically allowed region. This is for S waves. As you can see, all the region is allowed classically. So the S wave can enter from the outside into the black hole region here, and then it can come back to the infinity. Therefore, we can expect this type of S wave can express collapsing matter as an excitation. On the other hand, the Bohrs with large angular momentum have this type of momentum square. The point is here, interior part. This region is disconnected from the outside. So such a higher partial waves emerges as a bound mode independently of the initial state of the collapsing matter. In this sense, or this emergence of the bound modes is universal. Therefore, we can expect the candidate state should be a state in which the bound modes are in the ground state, but the continuum S waves are excited to express the collapsing matter. In such a state, the energy momentum tensor have this type of the form. The first term comes from the ground state in the interior metric. The second term are coming from the excitation part. This second term is classical, so we can fix the functional form by using conservation law up to the amplitude. We will fix this amplitude later by solving semi-classical Einstein equation. So our next task is to evaluate this vacuum expectation value of energy momentum tensor. Okay, this is step 3. First, we solve our field equation, Klein-Gondel equation for each mode by our new perturbative method, order by order like this. Then using this perturbative solution and our dimension regularization, we evaluate regularized energy momentum tensor for all the component. This calculation contains all the modes. So as you can guess, this calculation is technical and very, very tough, but I succeeded. And next, we introduce covariant counter terms, this one, and then we renormalize UV divergences, and then we get finite value. After that, we also consider finite renormalization effect, this blue one. Alpha mu, beta mu are renormalized coupling constant at some energy scale mu. So, and indeed, alpha is a coupling constant of R square, and beta is that of R mu nu square. So, in this way, we have obtained all the components of renormalized energy momentum tensor. Here, I will show a little bit concrete solution, concrete values. For example, this is a leading order part. So it is order 1. So for example, here, the first term depends on the choice of alpha 0, beta 0 at energy scale mu 0. And it contains a non-trivial finite value C. On the other hand, the second term appears only theta theta phi phi component. These two values give a 4-dimensional Weyl anomaly in a consistent way. Okay, in this way, we have obtained all the components of renormalized energy momentum tensor and Einstein tensor. The point is, our candidate state and metric depend on 3 parameters. One is intensity, the second one is ratio, and the third one is amplitude. If we find the self-consistent values over these 3 parameters satisfying this semi-classical Einstein equation, that means we get the self-consistent solution. Indeed, we have it. These are the self-consistent values if the theory satisfies this condition. This is our main result. In this way, we have realized our basic idea as a self-consistent solution. the self-consistent solution shows large tangential pressure occurs due to the vacuum fluctuation of bound moles with large angular momentum. Indeed, this tangential pressure is almost Planckian. This large pressure stabilizes the object against the gravity, and this pressure breaks the dominant energy condition, and this pressure makes the interior non-fluid. But, as I said, this pressure is consistent with four-dimensional wide anomaly. The second point is curvatures. The curvatures are order of 1 over n. So if we have large n, that is, if we have many matter fields in the Lagrangian, then the curvature is smaller than Planck scale. So we need not quantize gravity. But of course, we cannot treat final stage of the evaporation. So we are assuming such a small black hole at the final stage of the evaporation is described by some bound state in quantum gravity and string theory, and it decays soon. But here, I want to stress here, our semi-classical Einstein equation, that is our self-consistent solution, can describes almost all part of the evaporating black hole. This is non-trivial and very new. This is final step, black hole entropy. Suppose we have our stationary black hole, this one, in the heat bath, and then by counting the number of possible excited states of S waves per radius r, then we can find this entropy density. Indeed, by integrating this entropy density over the volume, we reproduce the area law in this way. So this calculation implies the information is stored inside the black hole as excitations of S waves. Conclusion: we have solved full dynamics of four-dimensional quantum matter fields in the semi-classical Einstein equation, and we showed this time evolution. That is, the matter becomes a dense object, it is supported by the large pressure, and eventually it evaporates. The interior is locally AdS2 times S2, and the state is given by this one, and the number of excited states of S waves can explain the black hole entropy, and that large pressure comes from bound moles. That's all. Thank you very much.
Thank you. Now the talk of Dr. Yuki Yakakura is open for questions.
I'd like to go to your step 3, what you did. Can you go to step 3?
Yes.
Yeah.
Yeah, here.
Right over here. Yeah, let's go. Here we go. Now you said we renormalize the UV divergence to obtain a finite value right over there. That's very, very clear. And you're looking at the leading order part.
Yes.
And so then what I'm asking you is that this little term right over here, this is your leading order part, so you can have what you might call the UV divergence and a finite renormalization. And it hinges upon this value of C right over in here. Am I correct?
You're
I'm looking at your value, the leading order part. And you said the UTT0, the renormalization, H bar N 1920 pi squared N squared phi. Then you have 2C plus gamma plus the log, and you have
yeah. Okay, thank you very much. So the finite, yes, here, this is the answer. So as you know, and to get self-consistent solution, we have to choose finite renormalization effect satisfying this semi-classical Einstein equation. So we choose this type of our finite renormalization. Then here, this boxed part vanishes.
Yes.
Then the remaining part only here, second one. So
Okay.
so the second, so on the leading value is 0011, this guy. Yeah.
Yes.
I have a question. Hi, Yuki, this is George.
Hi, thank you.
Excellent work. Really very nice. I just want to understand a little bit the physics behind this proposal. So I think what you're trying to tell us is that the black hole is formed right, by collapsing matter that is approximated as some type of interpolation of spherical shells.
Yes.
And if you self-consistently solve this sort of semi-classical equations, then you basically get that you get the right entropy. You essentially erase the singularity and also erase the horizon, because presumably these solutions of self-consistent equations do not have horizon to begin with, right? So it's they're kind of like fuzzball-like, right?
Yeah. I think so. Yeah.
So and the states, right, that you count are essentially sort of semi-classical or S-wave modes of those collapsing states. So that makes sense physically, I have to say, for large black holes. The question I have is, do you have any understanding of the Hawking radiation? And second, is there some way to actually test this for large black holes? I mean, as a self-consistent proposal.
Okay.
Astrophysically.
Astrophysically, and for the second question, I have no idea, or explicitly, I'm sorry. So, and for example, maybe you know, on some people study some refraction effect at the surface, right? So and so and in future, I hope, or by calculating explicitly on some expressed observable in this or in my model, then we can check the consistency between this model and observation, I think. Yes.
Okay. What about Hawking radiation? Yeah.
Okay. So for the about the Hawking radiation here, but I don't have so much time, so I will explain a little bit. So suppose we have many shells like this, okay? So, and the many shells, and here, now we consider only S waves, just an approximation. Then we get this time evolution equation. Here, maybe you know, this is a Schwarzschild derivative, okay? So S wave is essentially just a two-dimensional, right? So, and we can get this simple equation. The point is, we can solve this coupled equation dynamically like this, and then we get this one. The point is, this red line, the system inside each shell evaporates, emitting pre-Hawking radiation with the same magnitude as the usual Hawking radiation. So in this way, even if we don't have a horizon structure, if we solve dynamically Einstein equation and our matter equation, then we get pre-Hawking radiation with the same magnitude of the usual Hawking radiation.
And everything is unitary by definition, by construction.
Yes, exactly. Right? Yeah.
Very nice work. Thank you so much for alerting me about this.
Yeah, thank you.
Thank you, Yuki. Yeah, now it's time for Julio Arecha to start his talk. He is from Institute of Astrophysics of Andalusia, Spain, and ultra-compact stars in semi-classical gravity.
Okay, thank you very much, and thank you for allowing me to speak here. Today I want to talk about a work in collaboration with my supervisors, Carlos Barceló, Raúl Carballo Rubio, and Luis Garay. It is called Ultra-Compact Stars in Semi-Classical Gravity. we have strong evidence that there exist extremely dark and compact objects scattered through our universe. And I want to begin by raising the following question here. Do these objects correspond to the vacuum solutions from general relativity? Those are the Schwarzschild and Kerr metrics. Because it is reasonable to think of these vacuum solutions as effective models that will break down beyond certain scales. The most obvious place to look for this failure of classical solutions would be in the vicinity of space-time singularities, where the curvatures of space-time become Planckian themselves and we lose a well-defined notion of classical spacetimes. But there is another region where we expect quantum deviations from classical general relativity, while we still retain a well-defined notion of classical spacetimes. And these regions are the vicinity of event horizons, as predicted by semi-classical gravity. What we are trying to do in this work is give account of these important deviations from the classical theory at scales of the size of the horizon, which are motivated by the energy of the vacuum from matter fields, and try to see how these corrections work when trying to construct ultra-compact models made up of some classical matter fluid. So, as simplifying assumptions, we are going to consider the following static and spherically symmetric line element, where the time component is the redshift function of the geometry, which measures the redshift suffered by outgoing null rays, and C is the compactness function, which is a ratio between the mass and the radius of concentric spheres. Semi-classical gravity, as previously we have been explained, is a theory of gravitation that takes into account the fact that vacuum energy gravitates. The object that captures this contribution is the renormalized stress energy tensor, which is a quantity very difficult to calculate in general settings. In fact, this hasn't been accomplished in arbitrary spacetimes. And what we typically do is consider models reduced by symmetry in order to obtain closed and simplified expressions for this renormalized stress energy tensor. Once you have derived this expression, you can use it as an additional source of curvature in your field equations. This object has to be evaluated in some vacuum state, and throughout this work, I'm going to consider the matter fields to live always in the Bohr vacuum state, which is the vacuum state compatible with both staticity and asymptotic flatness of the geometry. If one evaluates this renormalized stress energy tensor in the Bohr state, you find that it diverges at event horizons. So once you take into account the back reaction of this tensor into your field equations, you are no longer going to find eternal solutions that have event horizons. These are going to be replaced by something else because of the back reaction of vacuum corrections. There is an additional complication in the renormalized stress energy tensor, and it is the fact that it involves higher order derivative terms that yield third and fourth order differential equations as your equations of motion. So this is an evident problem, and what we do here, the approach we follow, is trying to further simplify this object so that it contains up to second derivatives in the metric functions. So we can continue solving our field equations in a self-consistent way in a more easy manner. This way, the way we do this is through the Poliakov approximation, which considers as the renormalized stress energy tensor that of a massless scalar field propagating in a 1+1 dimensional spacetime. I won't go into the details here of how we renormalize this quantity, but once you obtain it, you can promote this two-dimensional tensor to a 3+1 dimensional quantity by means of the following projection of its components. Here, the Latin indices take 2 values, and the Greek indices take 4 values. And in doing this projection, you have an additional freedom of fixing this multiplicative function here to be whatever you want. Typically, what is done in the literature is fixing it to be 1/4 pi r squared by dimensional arguments, and this yields the well-known Poliakov renormalized stress energy tensor. But this choice of radial function carries along some problems, because once you evaluate the Poliakov stress energy tensor on top of a stellar spacetime like that of a relativistic star, you find out that these components are singular at the radial origin. So the Poliakov stress energy tensor is not a good source to do back reaction studies in stellar spacetimes. What we did in order to solve this issue was distort this radial function by adding the following cutoff to the components of the renormalized stress energy tensor, whose strength is modulated by this cutoff parameter alpha. In doing so, we obtain a cutoff regularized Poliakov renormalized stress energy tensor that you can see that this distortion of the radial function induces a non-conservation of this tensor in the radial direction. But because we are working with static configurations only, you can always compensate this non-conservation in the radial direction by the introduction of angular components. And in the end, you recover a covariantly conserved and also finite renormalized stress energy tensor, which you can use to source your semi-classical equations. Now, let me turn to a different topic, which is that of relativistic stars. These self-gravitating fluid spheres, as you all may know, have a compactness parameter that is bounded from above. This is the well-known Bugdal limit. That states that for stars made up of a fluid of constant energy density, their surface radius cannot be located below 9/8 of their gravitational radius. If you want the pressure of this fluid sphere to be finite everywhere. The conditions necessary to derive this limit are the following. First, you need that the energy density of this classical fluid is a function that decreases monotonically from the origin, from the center of the stars towards the surface. Second, you need that the pressure of the fluid, the radial pressure, is greater than the tangential pressure. And last, you need that these fluid spheres are matched continuously with the Schwarzschild vacuum solution at their surface. Semi-classical corrections provide ways to violate all these three conditions. The first one comes because semi-classical corrections violate energy conditions and indeed generate negative energy densities. So in principle, this could serve in order to violate this monotonic decreasing of the energy density, in this case of the total energy density, the sum of the classical plus the semi-classical parts. And you could, in principle, violate this condition. Secondly, renormalized stress energy tensors are anisotropic, and you could try to see if this anisotropy is sufficiently great as to violate the second condition. And finally, since you are considering now that the quantum field is propagating on top of your geometry, the exterior portion of the spacetime, the vacuum solution, is no longer vacuum, and it is not Ricci flat, so it doesn't correspond strictly to the Schwarzschild exterior. So you have these three different ways to violate the conditions that lead to the Bugdal limit. Now I want to introduce another aspect which is of importance in order to understand semi-classical stellar configurations. And it is that we have named criticality. The field equation for the compactness function, the temporal Einstein equation, can be analytically integrated to yield the following relation between the compactness function and the energy density, plus an additional term, an additional constant that appears as an integration constant. Depending on the value of this M0, we find three different configurations, and we refer to a configuration or a particular solution as critical when it corresponds to a separatrix between two very distinct changes in behavior of the compactness function. And this happens precisely in this context for M0 equals 0. This idea of criticality can be better understood by noticing the following relation between the ADM mass of the geometry, which is the mass measured at the asymptotic regions of spacetime, and the outcome of this integral, the integral of the energy density of the fluid, which is uniform here, to the whole volume of the sphere of fluid. If the outcome of this integral is exactly the ADM mass, then M0 is equal to 0, and you have a critical configuration. If, on the other hand, the energy density is smaller than this critical value, this defect of mass has to be compensated by the addition of a positive M0. And conversely, if you consider an energy density which is greater than the critical value, you need to compensate this excess of mass by adding a negative M0 here. Now let me show some numerical plots to illustrate how these solutions behave. For the subcritical regime, what happens is, you can see it in this figure. Here I have represented in green the areal radius of concentrical spheres in terms of a proper coordinate L. In blue, you have the compactness function, and in red, you have the classical pressure of the star. And you can picture this as the shape of the star as you approach the radial origin. For densities smaller than the critical value, the perfect fluid perceives a greater amount of mass than the one generated by its own energy density, and it enters a runaway tendency in the pressure, eventually leading to a singularity. If you keep increasing the value of the energy density, you find a critical value. You enter the critical regime, where the compactness is vanishing at the radial origin and the pressure is maximal. This critical solution is entirely regular because its compactness is smaller than the one stated by the Boogdahl compactness limit. If you consider objects with greater values of the compactness at their surface, you are going to find that the pressure diverges at some radius inside the star. And the radius at which this divergence takes place moves outwards as you compress the surface of your fluid sphere. Now you can keep increasing the energy density to enter this supercritical regime, where now the perfect fluid in this integration inwards from the surface perceives a negative mass, and the repulsion exerted by this negative mass helps the fluid towards attaining equilibrium. And you can see this in this figure, where the pressure is always finite everywhere inside the structure, and it reaches the equation of state of vacuum energy. It goes to minus the energy density at the origin, where you still have a curvature singularity because of this divergent behavior of the compactness. So now moving on to the main results of our investigation, I want to make some observations before analyzing stellar configurations. The first one is the fact that the semi-classical Schwarzschild counterpart is now an asymmetric wormhole, which has its event horizon replaced by a wormhole neck, as you can see here. This neck connects an asymptotically flat region with a new asymptotic region which has a singularity located at finite affine distance from the neck. As you can see here, the redshift function of the geometry is finite and positive at the neck as well. Now we have three different regions where the surface of stellar objects can be located, and these regions are above the neck, beyond the neck, and at the neck itself. Here in this talk, I'm just going to refer to stars located above the neck for simplicity, but in our work, we have considered all these three possibilities. And we are going to focus on super Boogdahl configurations, which are those whose compactness is greater than the classical Boogdahl limit. It is so because in most situations, semi-classical corrections over stellar spacetimes are completely negligible because they come with this h-bar factor here. But as you take the surface of your fluid spheres to approach this neck, semi-classical corrections become comparable to those of the classical stress energy tensor, significantly affecting the dynamics of the solutions. There is an additional comment I need to make about criticality in the semi-classical theory, and it is that now the critical value of the density is unknown because we do not know how to analytically integrate our semi-classical field equations. We can show this equivalence, which is similar to the one you saw in the classical case between the ADM mass and this integral, which now extends from 0 up to infinity, because we have an additional source of mass which comes from the renormalized stress energy tensor, and that extends up to infinity. Now, what we need to do in order to find the critical value of the density is to perform a numerical exploration, take different values of rho and see which of these values corresponds to a gross change in behavior in how the compactness function behaves. And this is what we have done in our work, and I turn to summarize our results. For the supercritical regime, the solutions are very similar to, in fact, are wormhole solutions, but now filled with matter fluid of some sort. Here you can see a zoomed plot of this region here, where you can observe this wormhole neck that connects the surface of the star with an asymptotic singularity. Now, as you keep increasing the energy density of the classical fluid, the size of this wormhole neck, the radius of the neck, shrinks. And you can eventually enter in what we have called the quasi-regular regime, which is a family of solutions that has extremely tiny wormhole necks compared to the overall size of the star. These extremely small wormhole necks also, as you can see in this figure, the compactness function crosses 0 here very close to the neck. So you can construct families of geometries which have arbitrarily small masses, arbitrarily close to the radial origin, because the wormhole neck can be made as small as desired in the limit that the energy density approaches its critical value. So we found this quasi-regular regime, which is not entirely regular, but it is in this sense very close to regularity, because a modification of the mass function in a vicinity of this core could suffice to regularize the whole construction. We argue that this failure of attaining equilibrium in this solution can be attributed to the intrinsic failure of the Poliakov approximation in appropriately estimating local contributions that come from local vacuum corrections near the radial origin. Whereas this approximation computes sufficiently well non-local contributions that depend on the vacuum states, it fails at these distances. So this is why we think these quasi-regular solutions are not regular in the first place. If you keep increasing the energy density, you find a critical solution which is singular. And for the supercritical regime, for rho greater than the critical density, you find solutions which are essentially identical or very similar to those from the classical theory. Now I'm just going to summarize my talk by saying that in the semi-classical theory, we haven't been able to find a strict definition of the Wulftal limit, and instead we have relaxed this definition, allowing to find families of solutions which describe ultracompact and horizonless objects, which are regular up to a central core of Planckian radius. Beyond this core, the solutions enter in a singular regime. This picture also tries to illustrate this in the sense that I'm showing a family of subcritical solutions which approach this quasi-regular regime, and by increasing the energy density, what you do is shrink the radius of this wormhole neck, also diminish the rate at which the pressure diverges, and eventually enter into this quasi-regular regime, where we wonder if this core can be regularized under different choices of the radial function f, or if this is not the case, maybe it can be regularized when considering more accurate approximations to the renormalized stress energy tensor. And this is currently what we are investigating. So here I end my talk. Thank you very much for your attention.
Thank you, Julio. Thank you for a nice talk. And now please ask questions.
I have one very specific question. Go to your last slide.
Yes.
Last slide.
Here.
You say in semi-classical gravity, there is no strict Bouchardal limit. Is this because of the issue of semi-classicality that you would be put into, like example, the Einstein equations, everything sort, or is it just something that would only be solvable to say in a fully quantum treatment of gravity?
Well, what we really found, we were unable to find a strict definition of the Bugdal limit in the sense of how you find it in the classical theory, that you find a strict value of the compactness that results in your most compact and regular solution. Here it appears that how you fix this Bugdal limit depends strongly on the kind of semi-classical matter that you're putting in. So you have this ambiguity here. And also the other aspect I wanted to emphasize is the fact that you can relax this notion of a strict regularity to imposing regularity on a Planckian core. I'm not assuming that the solutions are regular throughout the whole geometry, but they are regular up to some radius, beyond which I don't know what happens. So in this sense, we have found, that's what I was referring to, for that we haven't been able to find strict Bugdal limits. Instead, what we have found is this pseudo-regularity behavior. I don't know if that answers your question.
Yes, thank you.
Okay.
I have a very simple question. You talked about Poliakov renormalization procedure. What is the meaning of cutoff in the three-dimensional case?
I was referring here, there are two things. First, the renormalization procedure of your operator, of your stress energy operator, which is a covariant point splitting. And there is this another aspect, which is a cutoff to the components of the 3+1 dimensional tensor. This cutoff is only imposed once you lift your 1+1 dimensional tensor to a 4-dimensional spacetime. So these are two separate aspects, this renormalization of the operator, because you have to renormalize it in order to obtain a well-defined operator. And there is this second aspect that when you approximate it to be the stress energy tensor of a 4-dimensional spacetime, since the 2-dimensional tensor doesn't have information about the notion of spheres, you need to add this multiplicative factor, which is divergent in most cases. So the approach we followed is that what I mentioned, just put a sharp cutoff in the components of the stress energy tensor, which is the most simple thing you can think of in order to obtain a well-defined tensor in 4 dimensions here.
So lambda p is not involved in any equation.
What do you mean, sorry?
Does any equation contains this cutoff?
This alpha, you mean?
Yeah.
Yes, it is. I didn't show it, but it is inside every equations because you are doing self-consistent analysis.
Mm-hmm. Okay.
So this cutoff is put inside everything, yes, and it affects in some way.
So you're
solution.
saying your alpha term you get would be your H bar, that T nu B in the bracket. That alpha
yes.
term, yes, that alpha term was when you went to the prior equation was you the H T nu B in the bracket, and that would really be dependent very much upon some of the information that's given physically by the alpha.
Yes, and that's the point. That the physics of the center near the radial origin depends very much on how you regularize this object. In fact, it depends so much that if you consider only the Poliakov tensor, you do not find any regular solutions at all. But if you consider a cutoff, you find the equivalent of the classical stars, the classical neutron stars, perturbatively corrected by these corrections. So yes, it is very important, this point.
Okay, thank you very much again. The next talk is Andrew Beckwith, Generalized Heisenberg Uncertainty Principle in Quantum Geometry.
Well, this is perhaps the simplest minded of the
okay,
this is perhaps the simplest minded of the talks. So let me see. This is a GUP. You see it?
Yeah.
You
So
see it, gentlemen?
Different talk, yeah?
Yeah, well, this is the simplest one of the talks presented. Everyone else is far more technically savvy than I am. I don't mind, but let's proceed. refine the Unruh metric tensor uncertainty principle by the Schwarzschild geometry and Planck space-time was initial non-zero. I'm trying to move this right over here, non-zero entropy. Okay, yeah, that's a little better. Okay, sorry about this. I was just, yeah, my computer's been acting up. All right. Now, first of all, we restate a proof of highly localized special case of a metric tensor uncertainty principle first written by Unruh. Unruh did not use a Robinson-Walker geometry, which we do. And it so happens the dominant metric tensor will be examined as variation and right over here. The metric tensor variation is given by this, and this are negligible as compared to this particular variation of delta t, variation GTT. Also was referred to by both the emergent duration of time, delta t from the Heisenberg principle applied to delta GT in such a way to give the Planck spectrum a non-zero minimum, lower minimum non-zero lower ground mass for a graviton. The lower ground, lower bound to the graviton is influenced by GDT and a kinetic energy. All right, now I have to move this right up here. My screen's acting up. It's not you. All right, so that's, let me proceed with this. All right. All right. Keywords: massive gravitons, Heisenberg uncertainty principle, Riemann Penrose inequality. All right, we can skip this. Let me, this is just what is known about gravitons. And this is a very classical set of arguments. And this itself is straight. This is just very, very basic about how you can look at B graviton C and how 2m graviton C squared E graviton is equaling to that quantity. And the delta TE is the difference in the emission time in the case of the early universe near the Big Bang. So it's a delta TA and delta TE. Now, let me get to the main point of this. Otherwise, we're not going to ever get out of here. Note this comes from a scale factor is Z is 10 to the 55. A scale factor 10 to minus 55, 55 order. It's a magnitude smaller than what we would normally consider. But here, note that the scale factor is not zero, so we do not have a space-time singularity. We'll discuss this point in the next session of the non-zero smallest scale factor. Now let's go straight to the Unruh derivation. This is straight from Unruh right over here. And this is what I worked with. UVTT. So this is what this is variation in the metric tensor G nu V H bar squared over A volume. And this is straight from Unruh. There's nothing particularly very revelatory about it. Non-zero scale factor initially, and what this is telling us physically, starting with the configuration with Unruh, delta L, delta P, H bar. Well, this is again Unruh, and delta L, a delta variation of Gij for Gij to 1/2, delta P, delta T. So then, which is if we use the Robinson-Walker metric, and if we assume a very small scale factor, and if we use a 4-dimensional volume, right over here, we get delta GTT times delta TTT, H over B4. This equation 11 is such that we can extract up to a point the HUP principle for uncertainty and time and energy with one very large can be added, which is where you're going to have to use the fluid approximation of space-time. This is something where all you can notice and say in effect, okay, Unruh right over here, this is straight Unruh right over here. Plus I said the difference between me and Unruh is that he had something very similar to this is B4, but the B4, what I am referring to right over here is near the beginning of the early universe. Secondly, what I did was I used the TII in terms of a fluid approximation, which may or may not be valid. And that came with the delta T, TT, a variation density, delta E over V3. And so then this is my result, delta variation time, delta E, H bar GTT, which is not equal to H bar over 2. Unless you fit delta GTT would be approximately, parameterized to being 1. Well, that really isn't going to necessarily happen. All right, well, let me get to the rest of this. In fact, we had from Giovanni that if phi is a scalar function, a squared 10, then it's delta GTT is a squared T phi, much less than 1. There's no way that equation 14 is going to duplicate the traditional value. So it said that's a major divergence. And how can we justify writing very small delta GRR, delta G theta, delta phi going to 0 values? Begin with the process. We break it down in the following coordinates. And here I'm using the fluid approximation. And this is what I did right over here. R, theta, theta, and phi coordinates. We use the fluid approximation. This is key to my derivation. And this is what I was able to get in terms of the limits. All right, all right. So then what is it? If, as example, we have negative pressure with TRR, T theta, and D phi less than 0, and pressure equal to negative density, then the only choice we have is to then set delta GR, since there's no way is 0 valued. We're not assuming a 0 value in that situation. Now, then what I said, this is my case of using Barbour, use lower bound to the graviton mass using Barbour emergent time. And this is how I said emergent time, M a graviton, LP, to E energy minus a scale minus a potential energy term. And so that what I was able to come up with was M graviton is greater than or equal to 2h bar. Here's this scale factor LP squared. You have the total energy minus the potential energy plus this term right over here. The key to equation 19 was identification of the kinetic energy, which is written as E minus V. So we're talking about a kinetic energy, which is a major departure. So what I did was I said, well, what I said was the kinetic energy would be approximately equal to the early universe phi dot squared, a scale factor, which you could pick proportional a to the minus 6. This is done with the proviso that W is less than -1, saying that during the regime of Planckian space time, we consider a density proportional and call this kinetic energy as proportional to what was, what I'm referring to. Now, which is that here we have P of W, A, 3 months. If we were writing a small Planckian regime in space-time, we could then write equation 21 is proportional to this 21 is proportional to G star T47 with G star. This is degrees of freedom. Okay.
Hello. Hello.
Hello.
Anybody hear me?
Huh?
Anybody hear me?
Oh, yes.
Hello.
Oh, hello.
There is a loss
yes.
of.
Oh.
Where is our speaker, Andrew Beckwith?
I think you opened the breakout rooms. You invited everyone to the breakout room, and I think that he might have gone into a breakout room.
Breakout room. So let's close. So I'm sorry.
Huh?
Let's close breakout room. Close. Hello. Where is our speaker? Yeah.
I think he's still in the breakout room.
But I closed it. He mentioned that there is a problem with computer, but okay.
The basic thing which I did was to refer. So you didn't think I was just a madman, is the fluid approximation of space-time.
Andrew.
Yes.
Can you hear me?
Yes, I can.
Something happened, so you should repeat probably what you said during 3 last minutes.
Okay. All right. I apologize. It's just I had problems. I'd had problems with my computer. What I said.
I don't see you talk. Yeah.
Yeah. What I said.
Hear you.
Can you hear me now?
Voice, yeah, but I don't see your talk. Try to share your talk.
I am going to try to share it. Here, wait a minute. Okay, and I was okay. I'm going back to this. Yes. Right. Do you see it now?
Yeah. Yeah. Please repeat what you said during last 3 minutes because we lost.
Okay. What I was saying is that when we pick that delta T term, if you had a multiverse term right over M graviton, L Planck, and this is the kinetic energy term right over here. This is with respect to the number of different universes. This is respect to an averaging procedure, which you would add in. Okay, which you would add in is that then what you could come up with is a procedure that say where you might up to a certain point of time due to the uncertainty principle as stated, even though it would have a massively large right-hand term inequality, come up with something proportional to a square of the frequency, Planck initial, and this is to the -2, and this would right over here, a scale factor over the square root of 6.5 and 6 pi. Now, which is that what I want to do for further research is to stretch energy as the modified field equation. And here we can look example like Tij is equaling to these terms right over in here. This is one of the things that has been done in space-time physics. And I have been looking at different candidates for what the Gij are based upon the arguments which I did in the early universe. And I am referring to it's delta E, delta T, delta E, A bar, variation respect to the time component, the number of terms, a number of different contributing multiverses, A bar. Here would be an inversion factor, which you would get. This is an inversion factor, which is a renormalized reset contribution to begin of Penrose cyclic conformal cosmology. I've written a lot of papers on this. All right. And what I'm saying is that here we have something, here we have this. Now, which is that what I would like to work in the future has to do with, it's a delta 1 over n, this gamma right over here, and this inversion, this gamma right over here in inversion has to do with a reset from many black holes contributing, gathering matter energy and sucking it back. And then this inversion procedure was put into as far as the reset of the GTT term. But this itself is not equaling to this right over here, which is that there you have what you might call, you have to consider that there may be either one variation with respect to time which showed up in the early universe, or that there are many of them. This is the question that has to be answered. The other question has to be answered has also to would be if you had gravitons or something else that have occurred in the beginning of the universe, what type of scale factor contribution would you be looking at? This is -2 right over here. And when I'm saying this approximation would no longer hold, when you consider this right over here, this approximation would no longer hold. You have a more nuanced picture in terms of frequency from the early universe. Now, which is that what I was referring to about the old universe would be inverted, and you have the new universe is phi UV inverse times the old universe, and you'd have this inversion. The old universe inversion. This is what you might call cyclic conformal cosmology right over in here. And so this is a knit. I'm referring to something right over in here, which is they will show up in further refinements of this uncertainty principle and how you would evaluate it. This has to do with the generalization at Penrose cyclic conformal cosmology. Now, I really have run out of time. I have to stop because I'm not going to be fair to anyone else as I keep on talking. I have to stop. Can you hear me?
Yes.
All right. Do you have questions?
Yeah. Thank you, Andre, for your interesting talk. Please ask questions.
Well, I'm going to ask you a big one myself because I have a huge question. You see this delta GTT, this right over here. This is saying in effect, which is, if this is referring to when you use variation of GTT, this is referring to, you have 1 over n, you have n number of cyclic universes that are being renormalized or reset. Here is the reset of the geometrical factor, all right? This delta GTT, as I outlined for the uncertainty principle, this is with respect to individual contributions, all right? Here, which is that this is not the same thing as come up with a generalized state. We just have a one generalized delta GTT right over here. This is a big issue. This is a really, really, really big issue. And the reason why it's important, why I have talked about the bounding of a graviton and other things of the sort, is it really gets to the guts in terms of how we would pick this. What is this delta DTT? If you can't generalize this, say there's only one delta GTT, which is in the early universe, a squared is phi, much less than 1, okay, in the situation, is that how do you interpret delta GTT? You have just the simple repeating universe of Penrose. I'm saying that delta GTT may be different for different type of contributing universes if you have a recycling point. This is going to add further complexity and other things of the sort to looking at this relationship. This is essentially almost saying we just have one dominant universe and a Penrose recycling, and we have a well-defined delta GTT. But we may, if we have a multiverse, have something which is a more nuanced picture to the delta GTT term. And I'm saying this is something which I have to try to see if there's a phenomenological answer to this. You understand what I'm saying? Do you understand what I'm saying?
Yes.
Yes. And it's very, very important because I have M graviton delta GTT. Here I have this right over here. And this is what I worked out. And this is the lower bound Chapraptic, and this is with respect to inversions. But then when I say, oh, we go through all this, that's great. That's peachy. And we can generalize the uncertainty principle further. Oh, that's great. Thank you. Thank you, God, for letting me do this. All right. But then we have the conundrum. And the conundrum is the following. This thing right here. You understand what I'm saying? It's called, I started looking at the uncertainty principle in the beginning of a universe expansion. The delta GTT, due to this particular issue right over here, may be a lot more complicated than I think. I just said, well, I had a scale factor and I had something like an inflaton, which I put in, which may be a first approximation. Oh, that's great. What are you going to do? Example is you want example talk about transitions from prior, when you want to talk about transitions, let's say from a prior universe to the present universe, and you want to talk about, does this factor right over here, equation 32, say something about the growth of inhomogeneity that may occur, which is almost smooth, but it's not. Well, this right over here may to a certain degree accounting for initial inhomogeneity of initial conditions and some sort of a fluctuation of space-time. You understand why I bring that up? Roughly.
Okay.
This N is referring to the number of different contributing universes. You had a recycling of the Penrose argument, a multiverse generalization of. Here's an inversion factor. Here you have delta GTT. This, though, generally would, in most cases, would not be equaling to this, where you just simply say, well, delta GTT is just going to be uniform. This could be a different delta GTT for different contributing initial contributions to a multiverse. So in other words, what I'm saying is that what I am referring to here may have a lot more additional refinements ahead of it. Do you understand what I'm saying? And it may answer a question. It may be a way again at the initial inhomogeneity problem of why you have something that's so smooth, and how does inhomogeneity actually occur in the first place? And the question is that we have something like a very small delta t, which is time, a very small delta t, maybe Planck time or something, delta E. We have something that's more complicated right over here. Some sort of generalization of this to a multiverse, which I am trying to work on, may tell you something about how you literally nucleate something from nothing, so to speak, which is a delta E. And in addition, after you do this, is say something about the initial growth of inhomogeneity. That would be my hope. And I'm no genius. I just merely am just working with what the math says. So I hope at least that I've given you food for thought. You have my paper, and you can send me email and question me to death. I invite everybody that rwill9955b@gmail.com is that you have a copy of this. Send me email, and I will try to defend it. And secondly, too, after not only trying to defend it, what I will try to tell you is how I might be able to say something about the growth initially in homogeneity, which itself is not really understood in terms of quantum. It's not really understood in terms of the quantum universe. Where did inhomogeneity of the expansion start in the first place? So far, I don't have a convincing answer to that. You understand why I raised that question?
Okay. Yeah. So probably time is over. Thank you.
Yeah, I'd run out of time. I hope I didn't bore you. I wasn't trying to bore you. Did I bore you? I apologize.
Yeah. So thank you very much for your talk. And the next speaker is Koen Yamamoto.
Yeah, I'm going to have to go to another one. Could you just wait? Let me just get you. I'm just trying. I'm being very, very clumsy. How do I open this up? I need to sign out, and it's not because of you. It's because I have another talk. I have another talk about artificial wormholes, and I have to get ready for that one.
Okay.
And I just don't want to get, okay. So anyway, I wanted to say thank you very much. I'm not, I really like what you're doing. I have to prepare for another talk on experimental gravity. And
Okay.
please send me email. Do you understand?
Yes.
If you had complaints and everything, send me email. And secondly, if you don't like what I'm doing, you have the default option. When I send in my conference proceedings, you can kick it out, Lebed, and I won't take it personally. Do you understand? No problem. Don't worry about that. But I have actually published in the Ukrainian Journal of Physics. I've done work in the Ukraine with this particular item. You understand what I'm saying? I've done work in the Ukraine with this, and I talked to several Ukrainian physicists in the Lebed and Bogalukov Institute, you know where that is, in Kyiv. And I've been there before, so I discussed this at length. Do you understand?
Yeah, okay. Okay, so we need next. Yeah,
thank you very much. Thank you very much for your patience.
Thank you.
All
so
right.
it's Koei Yamamoto, Einstein anomaly with tensors of odd order in 6-dimensional space, curved space. Kumamoto University, Japan.
Hello, I'm Kohei Yamamoto from Kumamoto University. I will present our work on.
Could you speak a little bit in loud voice?
Oh, Einstein anomaly with tensor of order in 6-dimensional curved space. And this is an outline of our presentation. First, I will provide some information on Einstein anomaly in 6 dimensions. Next, I will describe heat kernel. After that, I will describe Fuji-Kawada method and covariant Taylor expansion. There is use for calculating Einstein anomaly. Then I will show you the result of Einstein anomaly calculation. Finally, I will show you calculation, a conclusion. To begin with, let me give you some background about our research. By applying the covariant Taylor expansion method of heat kernel, Einstein anomaly associated with wire fermion of 1/2 interacting with no abelian vector field in 6-dimensional curved space are given. From relation between Einstein and Lorentz anomalies, all terms of Einstein anomalies should form total derivatives. Einstein anomaly, Lorentz anomaly. It is shown before as trace operation of the gamma matrices, and the Einstein anomaly is expressed by form expected. In this study, we tried to calculate Einstein anomaly, adding tensor of order 3 as a new interaction term. Next, explain about heat kernel. Heat kernel is used for calculating concrete form of anomalies. Heat kernel K is for fermion is defined as parabolic partial differential equation and initial conditions. H is defined as a d slash squared. D is defined as this. Other terms are defined these. Omega is spin connection, and B is the vector field. It is difficult to obtain exact form of heat kernel for fermion. In order to evaluate heat kernel, With answers usually applied to heat kernel. Sigma is world function. It is equal to a half square of the geodesic distance with between x and x prime. Delta is the determinant. It is different as this. AQ is a coefficient. Coefficient limit is defined as this. It denotes square bracket. Sigma is sigma of coefficient limit of sigma is this, and other term is this. Example. By applying coefficient limit, heat kernel is given. Now I would like to move on to the next page. Next is Fujikawa's method. Formal expression of Einstein anomaly is obtained from path integral of a half-rounded fermion. It is represented by a heat kernel after regularized by Gaussian cutoff differentiation operator. Semicolon means covariant differentiation with vector gauge transformation in curve space. Exclamation mark means the modified covariant differentiation. After that, I will explain about heat covariant Taylor expansion. Differentiating the world function by d and d mu dash obtained there. Using these, we define eigenvector and inner product. Eigenvector and inner product are defined as these. AQ rewritten by eigenvector and inner product is this. I is translation operator of spinor. Get AN is defined as this. Get N AN is this. It is used for calculating coefficient limit of AN. These are examples. Each term, by calculating each term, Einstein anomaly in 6 dimensions are given. Finally, I will calculate Einstein anomaly associated with the wild fermion of spin 1/2 in interacting with non-abelian vector in 6-dimensional curved space. X and lambda are expressed in vector field. F mu nu is defined as this. Trace of gamma 7 and trace of gamma 7 gamma mu nu is equal to 0. Therefore, trace of gamma 7 x and trace of gamma 7 gamma mu lambda mu nu are equal to 0. Terms contain x and lambda of 1 degree do not contribute to anomaly. 2 or more degrees are x and lambda of 2 or more degree are contribute. As a result, Einstein anomaly in 6 dimensions are given. J is defined as this. R is Riemann tensor. From the relation between Einstein anomaly and Lorentz anomalies are all terms of Einstein anomaly should form total derivatives. It is shown before the trace operation of gamma matrices and matrices that the anomaly is expressed. Gamma matrix. I would like to move to next page. Einstein anomaly adding torsion as the interaction form. Y is replaced by Y prime. C is torsion tensor. It is completely unsymmetric tensor of order 3. Then x and lambda are written in x prime and lambda prime. Important point to note is this. Trace of gamma 7 squared is not equal to 0, but because of unsymmetry of relativity tensor, this term is equal to 0. Therefore, trace of x prime and trace of lambda prime are equal to 0. Containing x prime and lambda prime of 1 degree does not contribute to the anomaly. As a result, torsion does not modify Einstein anomaly. In conclusion, tensorial form of Einstein anomaly in the presence of torsion should be derived by replacing x and lambda mu with x prime and lambda prime before trace operation. Future work, we calculating the tensorial form of Einstein anomaly in 6 dimensions. We will try to confirm that the all terms of Einstein anomaly form total derivatives x and lambda terms in higher dimensions. That's all my presentation. Thank you very much.
Thank you, Kohi. So the talk is open for questions. Yeah, please ask questions. Can you hear me?
Yes. Yes.
Okay. So this means that there is no questions, and the next Speaker is Maximilian Heinz Rueb, and the talk, Casual Measurements of Quantum Fields with Local Probes, University of York, United Kingdom.
Thank you very much. Can you see my slides?
Yeah, I can.
Perfect. Okay, good. Then I start. So thank you very much for this opportunity to talk about my work here. My name is Maximilian. I'm from the University of York, and I'm a PhD student there under the supervision of Chris Fuster and Henning Bostelmann. And I'd like to tell you something about our work, in particular about causal measurements of quantum fields with local probes. So let's get right into this. This is the outline of my talk. I'd like to first talk about problems of measurements in relativistic quantum field theory on a fixed background, in particular about these things like instantaneous state collapse and superluminal signaling that you might encounter there. So all the problems that you have in that direction. Then a second point is quite some cut. I would like to talk about just measurements with probes. This is a very general story with which you're probably familiar from quantum information. So very general. The third topic is then how to apply these local probes in a quantum field theory setting. So in particular, we will talk about or emphasize the importance of the locality and the causality of the coupling between a probe and a system in order to perform measurements, which is the fourth point. And there we will in particular talk about the causality of measurements, and we will also talk about how state update rules, which are usually put into a measurement theory, are actually emergent in this setting if you describe measurements with probes. And then at the end, there will be some outlook and hopefully a discussion. So let me talk about the problems of measurements. So first of all, the problem with measurements on a fixed background in relativistic quantum field theory is, or one of the problems is, that there is no objective simultaneity, okay, which is in particular a problem for statements like this in the quote. So local measurements, non-selective, are followed by state updates, quantum operations, okay? And in some sense, in my talk, I will maybe not challenge this widespread statement, but at least comment on maybe how you could interpret this and what the right setting is in which you should take this statement here. Good, but maybe now let's take it how it is. Let's say that okay, we work with state updates after non-selective measurements, quantum operations. But then of course this absence of an objective simultaneity, this basically the different options that we have to follow space-time yields the following problem. So suppose we have the following situation where I have two observers, Alice and Bob here, some finite spatial extent and some finite extent in time direction. So here this is the region of control of Alice and Bob, let's say. And I also have Charlie, such that Alice and Bob are space-like separated, and Charlie is in the joint future of Alice and Bob. Okay, and Alice and Bob perform a measurement, right? So Alice does something, Bob does something, and Charlie does something. And the question is, in what state does C measure if the quantum system, the quantum field, is initially in the state rho? So as I said, I follow this maxim. I do not question it further at this point. And I could, of course, update the state first according to the update that I get from Alice, and then Bob, or first Bob and then Alice. So the question is, what can I do? Okay. And the problem here is, of course, that there is no objective order between Alice and Bob because they're space-like separated, right? No clear causal order. What you can hope for is that if A, B, and C are causally orderable, which means that I can order them in some way that is consistent with causality. For instance, I can say that A is before B is before C, at least for some observer, at least for some foliation of this spacetime, for instance. Then I want to get the same answer for any admissible causal order. So in particular, I want to get for an expectation value of the observable of Charlie OC in the state rho first updated for Alice, then Bob. I want to get the same result as when I first update Bob and then Alice, right? And indeed, this is true because of basically space-like commutativity, Einstein causality, microcausality, however you want to call it. But nevertheless, it's in some sense messy because I have to find the causal order. I have to perform the state update by hand, right? First A, then B, first B, then A, depending on an admissible causal order, and it's quite messy. But in principle, at the end of the day, you get the right result. A more severe problem concerning measurements in quantum field theory is a Sorkin superluminous signaling problem, okay? Where you have 3 observers in this situation here, Alice before Bob, before Charlie. And now you have the situation that Alice and Charlie are space-like separated, okay? So we ask the same question in what is the expectation value of Charlie's measurement of an observable OC. And of course, here Alice is before Bob is before Charlie. So I first update with Alice's update, then with Bob's. But at the end of the day, because Alice is space-like separated from Charlie, whether Alice measures or not should not affect Charlie's outcome. So in particular, this equality here should hold. I should disregard Alice's update. But the problem is, as Sorkin showed in his 1993 paper, that this is in general not true. So this equality does not hold, in particular for projective measurements in the region A, which are very, very mild things to do, right? Seemingly mild, at least, to perform a projective measurement. So there is really a problem with measurement theory in quantum fields, okay? And we're about to solve this problem, or at least show an approach. For that, I want to talk about measurements with probes, okay? So heuristically speaking, operationally speaking, what is the idea? Well, you want to measure a system. How do you do this? You take a probe, which is a model of a measurement device. You couple it to the system for some amount of time temporarily. Then you look at the probe, a certain probe observable, and from that information, you infer something about the system. I like to use the example of measuring the temperature of my cup of hot chocolate, right? So I put the thermometer inside, I let it interact with the hot chocolate for a while, and then I take the thermometer out and I look at the thermometer and I don't know, I can measure the volume of the mercury or the alcohol in the thermometer, which is an observable of the thermometer, but then I can infer something about the property. I can infer something about the property of the system, that is the temperature of the system, right? And mathematically, I can take this heuristic idea in the following sense. So I take rho S, so the state of the system, I couple it, so I take the tensor product with a state of a probe theory, a probe quantum system, right? There's a probe Hilbert space there. Then I let it interact unitarily, of course. And then I look in the coupled system, okay, of a system and probe in the coupled structure. I look at the expectation value of the identity on the system and a certain probe observable. And then actually what I get is this is equal to the expectation value of a certain induced probe observable in the a certain induced system observable, so probe induced system observable in a system state, okay? So I can really say that when I measure something, when I look at the expectation value of a probe observable in the coupled structure, this is the same as the expectation value, with a trace over the system, of a certain induced system observable and the system in the state rho S. Good. So this is the concept of the induced system observable. And it's interesting that for a bipartite probe, there is also the concept of an emergent state update rule. Okay, so suppose I have 2 probes, rho A, rho B. Okay, I let them both interact, first Alice, then Bob, and I'm interested in an expectation value of a probe observable of Bob. Then I can actually write this in terms of an induced system observable associated to Bob and traced against not the state of the system, but actually an updated state of the system, right? So this is here the formula for the non-selectively updated system state. And this is interesting because in that sense, the state update rule is actually emergent, okay? So the left-hand side is the actual expression, the actual thing that I measure in a world where there is the system and the probe. And on the right-hand side, when I want to ignore the probe, I actually get the same result if I take the induced observable and if I take an updated state that takes care basically of all the probes that were previously there, in that case A before B. Okay, good. So this is the idea how you measure with probes, and it's important that there is one rule of the game, which is each probe is only used once. So if you want to perform a new measurement, you have to get a new probe. And this also means that you do not update probes. Okay, so the probe is really fundamentally different from a system. It's clear that this is not a final description of reality, where at the end you do not want to have a sharp cut from the outside between a system and a probe, but it's a first step. Okay, so after all, this is not intended at solving the measurement problem, but this is intended to be the first step in what Chris Fuster calls the measurement chain, or how he puts it usually. Good. So now let us apply this to quantum fields. So for that, we have to talk about what kind of probes we want to use when we want to measure quantum fields. And this goes back to a paper by Chris Fuster and Rainer Ferch, where they discuss or consider locally coupled local probes. So our input is consistent relativistic quantum structures on a fixed backgrounds are quantum fields. Okay, so therefore also fundamentally speaking, probe systems should be quantum fields. Okay, then the coupling should be local, because all interactions in nature are local, and only active in a compact coupling zone, basically meaning that the coupling is really temporary. Okay, and then multiple couplings should also respect causality. And they have a beautiful model independent and abstract discussion in their paper. And at the end, we basically get from this, we get local scattering operators that act on the system and the probe together. So those are basically the unitaries that we had on the slide before. And they have important properties, two of which are very important for us. So first of all, they act trivially space-like separate from the coupling zone, and they respect causal factorization. So let us have a look on the right here. Suppose we have Alice in this region of control here. She couples a probe, so one quantum field, to the system quantum field inside of this blue region here. We get a scattering matrix SA. To the future and the past, it acts via adjoint action. And space-like separate, it also acts via adjoint action, but it's a trivial action, right? So it acts trivially space-like separated how it should. And on the other hand, if we have Alice, Bob, and Charlie, so if we have a probe that is actually a tripartite probe, so we can split it into three parts, Alice, Bob, and Charlie, then we have one overall super scattering operator that is associated to just the set without any order of Alice, Bob, and Charlie, and then it factorizes according to any admissible causal order, right? So here I could say that Alice is before Bob is before Charlie, so I first act with the scattering operator associated to Alice, Bob, and Charlie, or I could say that B is before AC, and this is reflected in the other factorizing possibility, okay? And these two inputs are very important and will actually allow us to talk about measurements with probe systems on quantum fields, which is what we want to do now. Okay, so we talk about causal, emergent, non-selective state updates. So let us consider the situation similar as before. Okay, but now we have many causally orderable experimenters. Okay, so m plus 1 plus n, and we group the first m. We call them team Alice. Okay, then we have Bob, and then we have some team Charlie. Okay, the right hand side you could think of team Alice. All Alices are somewhere inside this blue region, causally ordered, such that A1 is before A2 and so on. And here is team Charlie, okay? And now we can ask the question, good, if Alice, team Alice, Bob, and team Charlie, if each of them performs a measurement, at the end, what is the expectation value of B's measurement of some probe observable OB? And as before, right, what do we have to take? Well, it's the trace over the super scattering operator against the system state tensored with Team Alice's probe state, Bob's probe state, and Charlie's probe state, and again the adjoint of the super scattering operator, and the observable of the probe tensored with factors of the identity. Yeah. Then we use causal factorization to split up the S matrix. Okay, we see that Charlie's action drops out, and then we use the definition of the induced probe observable and the definition of this, let's say, updated state, which are both given on the right-hand side here. And then at the end of the day, we arrive at this equation here, okay? So really, you can say that the final answer is really the expectation value of an induced observable given in an updated state, okay? And now here are the important points summarized. So first of all, the expression here on the right-hand side is automatically independent of Team Charlie, which is good, right? Because it means that there is no influence from the future to the past. Second, this non-selective state update rule emerges. It's not postulated, okay? So if you want on the left-hand side, this is the fundamental expression where we have all the probes and the system, and we can rewrite this in terms of an induced observable and an updated state, okay? Moreover, what we had before in the first or second slide, where we had an ordering by hand, this is not required here, right? So on the left-hand side here, I have a superscattering operator associated just the set of A, B, and C. I didn't have to order them. The causal factorization property basically tells me in what way I can order it, but I don't have to, okay? And this causal factorization property, this is also reflected in the fact that this updated state, this updated system state, yeah, associated to Team Alice, I can view this as the system state iteratively updated for LS1, LS2, and so on and so forth, okay? So this sounds very nice, very consistent, very covariant. But what about this superluminal signaling issue by Sorkin, okay? So suppose that one member of AJ of Team Alice, one member AJ of Team Alice is space-like separated from Bob, okay? So then in particular, the expression, the expectation value for Bob should be independent of AJ, okay? So instead of the A's that we have here, we would like to have A without AJ. So we want to completely ignore AJ. And indeed, when you look at our paper, this is true, okay? So really this AJ drops out. There is no superluminal signaling. There is no dependence on space-like separated observers as there should be in a fully causal covariant theory. Good. And in particular, you can also view this as the updated state. You basically just ignore the update that we had before according to AJ. So because of time issues, let me just flash this slide at you, which tells you that you can play the same game for emergent selective state updates, okay? Where basically on the joint system, on the joint structure of system and probes, you look at the conditional expectation. And then when you go through the mathematics, at the end of the day, you can rewrite this in terms of an induced observable and a selectively updated system state. But it's important that operationally speaking, this conditional expectation corresponds to a post-selection that all the observers do at the end of the day in their joint future together, okay? So that's why selective updates are unproblematic from a causality point of view, because they reflect post-selection, which can only be performed when all observers really meet. So that is an important point, okay? And again, it's important, this selective state update rule, it emerges, it is not postulated, and it can be rewritten iteratively as a result of successive selective updates. Okay, and maybe also one point here, the idea is that Bob conditions on a result of Alice, where Charlie is in the future, but of course Bob could also condition of a result of Charlie in the future, but then we would not expect any meaningful selective state update. If you condition on something that would happen in the future, you do not expect any meaningful selective state update. Okay, good. I'm on my last slide. This is my discussion and outlook. Let me quickly go over this. So what locally coupled local probes can do. So first of all, they provide a measurement theory if one follows the rules of the game. Okay, so we can discuss whether these rules of the game make sense, but I would say also in quantum mechanics, quantum information, they are state of the art. Okay, and most importantly, you use a probe only once, and probes don't get updated. Okay, so even in effective description where updates are emergent, the probes are not updated. They are the things that are discarded in this effective description. Okay, so non-selective state update rules are emergent. not postulated, and they are not even required. If you don't like state update rules, you don't need them. Okay, we just work with the joint coupled system structure of the system and the probe. Then selective state update rules, they are also emergent and are based on post-selection. So in particular, no causality violation by fiat, basically. Then the non-selective state updates are fully causal, as we showed. So they are an example of a causal quantum operation. And now it becomes interesting because this paves the way for fundamentally causal quantum information protocols on quantum fields. Okay, an example for that would be entanglement harvesting, which you can see in this preprint here. And then on the right box, there is, well, a little picture of what entanglement harvesting is, but for reasons of time, I think I can't get into this. And let me maybe mention other approaches to give credit to other people who are working in this field. Alternative approaches comprise UDW type non-local particle detectors. So you take this UNRO or UNRO-DeWitt type detectors, which are, I don't know, a qubit or a quantum mechanical harmonic oscillator, and you couple it to the system. The problem is, of course, they are not causal. Okay, so you have a non-local coupling or a singular coupling. So some causality is only approximate, which you can see in this paper 3. And there's another approach you can avoid, or you just not use any probes. There are those papers 4 and 5, in particular 5, a recent preprint, where they talk about really state update rules, which are causal. And then it turns out that those which are causal basically have the same properties as those that you get effectively from using probes. Okay, so there are some people who prefer throwing away the probes, throwing away this idea, just taking the effective update rule. This is interesting, but as I hoped I could argue, using probes is just a very nice way of describing measurements, of discussing the emergence of state update rules, not postulating them, and in particular of getting a causal measurement theory without any superluminally signaling issues. And this is the end of my talk. Thank you very much for your attention. Sorry for going over time. I think you're muted. No, you're still muted. I think, yeah, this is the sentence of the year. You're muted.
Okay. Thank you.
Now I can hear you.
Thank you for your poem. Thank you very much, Maximilian. Now, please ask questions. Yeah, what do you think happen in gravitational field? Because locally gravitational field is Lorentz invariant, but locally and globally different stuff. So what would you think?
Well, so as I said at the beginning, here this measurement theory concerns quantum fields on a fixed background. So this is really QFT on curved spacetime. So you're kind of tied in this scenario to some globally hyperbolic spacetime that is underlying your theory. So what happens with gravitational fields? Well, so if you're only interested in I don't know an approximate effect, yes, you could very well do this in something like effective perturbative quantum gravity, where you have this traditional split into some background, and then you have some small quantum fluctuations of the field, and then this machinery is expected to go through, basically, because you're then again in the setting of a quantum field on a curved spacetime. And if you want to go to real quantum gravity, of course, you generally have the problem of absence of a preferred background structure, and then also this whole question of observables becomes difficult. But the hope is still that exploring these probes, so that the way of measuring something of a system by coupling it to an ancilla system, to an auxiliary system, could still be promising in different scenarios, maybe also going into quantum gravity. This is the hope.
And very simple question. What does happen with Heisenberg uncertainty principle in this case? So there is no any principles.
Well, so so what you have is actually interesting. Okay, so let me yes, so it's this line here, the second line on the right upper box. Okay, so in the real world, what you would actually measure is the identity tensor, some observable on the probe. Okay, and you can effectively write this in terms of the expectation value of some induced observable against the state of the system. Okay, so now here on both sides, you will have some uncertainty. Okay, there will be some variances when you measure these observables, and it's interesting because the effective description that when you use induced system observables, okay, the variance that you get if you describe a measurement like that will actually be larger, and that is also intuitive, because what you pick up are basically the fluctuations in the probe itself, if you want. So you have some fluctuations because you're considering a measurement of a quantum observable anyway, but this fluctuation will become actually larger because you have a quantum probe with which you measure this observable. So you have a so I would say this idea of having the uncertainty principle and having some uncertainty there and some variances, this is also very much present in this. And that there's actually a nice paragraph in the original paper by Fust and Ferch about this, how the use of a probe affects the variances of the observable, and how you get an additional fluctuation from the probe.
Okay, thank you very much. Thank you very much one more time.
Thank you.
So we have almost time for the last speaker, because the thermalization of harmonic oscillations Unruh-Dewitt detector was withdrawn. So now I'm asking Sander Kolikar. Are you ready for talk?
Yeah, hi, hello.
Hello.
Yeah.
Are you ready?
Yeah, I can present my talk now.
Okay. Okay, so it's 2 minutes early. So you have 2 more minutes for questions. So quantum memory and BMC symmetries, University of Nottingham, United Kingdom, and Center for Excellence in Basis Sciences, Mumbai, India.
Yeah,
please start.
Thank you for that introduction, and thank you for this opportunity to present our work. So today I'll be talking about this work on quantum memory and its connection with BMS symmetries. So I'll just tell you what the brief outline is. So first I will talk about this gravitational memory effect and BMS symmetries, and how are they connected to black hole thermodynamics, in particular the information paradox. Then I'll talk about this Hawking-Perry-Strominger's claim of soft hair for black holes. And then I'll talk about a physical process version with which you can basically implant this soft hairs on a Schwarzschild black hole using shock waves which have basically non-spherical symmetry. And then I'll talk about what is the classical memory effect for uniformly accelerated observers. So we mostly know it for inertial observers, but then I'll define what we mean by memory effect for uniformly accelerated observer or Rindler observers in the Schwarzschild background space-time. And then I'll talk about the quantum version of the gravitational memory effect and how it basically amounts to redistribution of entanglement across the horizon. So these works are based on the papers which I have shown over here. Okay, so let me just give a very brief introduction of what the gravitational memory effect is. So as you can see from this particular picture, that if you have, let's say, a system of configuration of test particles, let's say far away from some source, and let's say a gravitational wave passes through this configuration. So in this picture, let's assume that it's passing perpendicular to the screen. Then we know, because of the stretching and contracting of the space-time, the mutual separation between the test particles is going to change as the wave passes. Now let's assume that after the wave has completely passed, that the system of configuration of these test particles, it doesn't return to the original configuration, but it is distorted in the way which is given over here. So once the wave has passed, we can say that this, depending on the change in the mutual separation, there is a memory retain of the passing gravitational wave. So this is the type of a displacement memory effect. There is another type, which is the velocity memory effect, in which, let's say, one of the or many of the test particles can get a velocity kick because of the passing wave. Now, of course, there are the linear and the non-linear types of memory. But for today's talk, I think I'll just say that we'll be focusing on the connection between this gravitational memory effect and the BMS symmetries. So what are the BMS symmetries? So if you look at asymptotically flat spacetimes containing a black hole in the interior, or maybe not any other gravitational source, but which are essentially asymptotically flat. And if you do this translations, okay, which are basically angle dependent. So if you can look at this Penrose diagram over here, and if you fix on this blue circle, so this is basically your future null infinity, and at that future null infinity, if you do a translation which is basically angle dependent, then this happens to be a symmetry in the sense that your metric just has a diffeomorphism acting on it, and the diffeomorphism vector is of this particular kind. So there is a particular function which is a function of the angular coordinates, and it basically, the leading order your metric is still flat. So you would have corrections depending on what are your fall off properties. But essentially, this basically uplifts the known 4 global translations that we know into an infinite number of diffeomorphisms, which are the super translations. And they are characterized by these functions. So what is the connection between these infinite number of symmetries, asymptotic symmetries, and the gravitational memory effect? So it was basically shown that if you act on the scenario which I showed in my previous slide, that if you have the system configuration of let's say test particles, and if you apply on them the diffeomorphism corresponding to this particular symmetry known as the BMS symmetry in the name of these particular people who discovered them, then you would basically change the effective distance between those two inertial particles. So there is a one-to-one correspondence between the memory effect and the asymptotic symmetries. There is also this third vertex, which are the soft theorems, Weinberg's soft theorems. And having these infinite number of symmetries, one could basically define an infinite number of charges, both at the past null infinity and the future null infinity. And then because of a particular antipodal matching, you could basically show that there are these infinite number of conservation laws corresponding to those infinite number of charges which you have. And then the ward identities corresponding to those charges, they are actually connected to the soft theorem. So in today's talk, I'll be focusing on the connection between the gravitational memory and the asymptotic memory. So how do we basically use it? So it has to do with this proposal by Hawking, Perry, and Strominger in the context of, let's say, the information paradox. So the statement is the simplest statement of information paradox is the following: that if you, let's say, have a star which collapses to form a black hole, and after it forms a black hole, it emits thermal radiation. So essentially, you begin with the pure state, And then after the evaporation, let's say you are just left with the thermal radiation. So you would have a thermal density matrix. And of course, you have broken unitary evolution somewhere. So if you were to have unitary evolution, you would like to show that there are these additional correlations in between the outgoing Hawking pairs. So yeah, so where are the correlations and how do these correlations essentially appear? So their proposal was, since you now have those infinite number of conserved symmetries, infinite number of symmetries and the corresponding conserved charges, perhaps now you have, in addition to the usual three charges which we know from the no-hair theorem, the mass, charge, and the angular momentum, now you have this additional number of infinite number of charges. Perhaps there is this information encoded in the outgoing Hawking radii as well. Now this proposal also has its own criticism, so I have mentioned here some references. But I'll focus on the point about how do the super translations essentially may affect the correlations in the outgoing Hawking pair. So that is what I'll focus on. So here is one process through which you can basically try to implant super translation hair on a black hole. So the process is by using a shock wave. The shock wave is now defined in a very particular way. So the definition is as follows. So you basically take the Schwarzschild spacetime, and to it you stitch another copy of the Schwarzschild spacetime, but that Schwarzschild metric has been applied by a BMS symmetry. So you take a metric, you apply the BMS type symmetry on that particular metric, and essentially you stitch them. So you generate basically a BMS type of a shock wave, and which is represented in this picture by this green line. So it's a null shock wave, which essentially passes through the horizon. And the important part about this shock wave is it doesn't have spherical symmetry. So it basically has angle dependent information about the wave. And as it passes through the horizon, the idea is that it's going to generate some non-trivial transformation or translations at the horizon, which is supposed to affect the outgoing Hawking pair. So that's just the idea. So what I'll focus on is, by doing a field theory calculation, I'll try to understand what happens between the entanglement in the Hawking pairs due to the presence of this BMS shock, and try to see how maybe the correlations are changed in the Hawking pair. So before I do that, I must talk about first the classical effect. Now, since this shock wave is going to affect observers also non-trivially, here in this case, we should talk about the uniformly accelerated observers, because those are the observers who are going to measure the thermal radiation from the black hole, the stationary observers who are at R equal to constant. So the first question to ask is, how does this BMS shock wave basically affect those observers? So just like in the usual gravitational memory case, once you have a gravitational wave passing through an inertial observer setup, we know that the mutual displacement basically changes. So the question here we are asking is, through the passage of this BMS type of shock wave, how does it affect the congruence of uniformly accelerated observers? So that would form the classical part of the memory. And then the quantum part would be when we basically talk about the background quantum fields and how it basically redistributes the entanglement between the Hawking pairs. Okay. So to whatever I have described just now in words, this is the same thing mentioned in terms of equations. So this is basically the metric which describes the scenario given in this picture. So in this metric here, H is essentially the Heaviside step function. So if this nu is less than nu naught, you have the standard Schwarzschild metric written in terms of the Bondi coordinates. And after the wave, you have basically the super translated Schwarzschild metric. So this is essentially the stitching that I was talking about. And here the function C of theta. So this is basically a function of the angular coordinates theta and phi. It basically captures the asymmetry of the shock wave, which basically falls in. The corresponding super translation vector is basically presented over here. And this is basically the change in the Schwarzschild metric, which I showed earlier. And this is the corresponding stress energy momentum tensor of the shock wave. So it is non-zero only on the wave, and otherwise it is the usual vacuum solution. Okay. Now, to do this complete calculation, I would also need to know what are the mode solutions in the Schwarzschild background, which are obviously non-trivial to work with. So what I will do is I'll use this analogy between the Hawking effect and the Unruh effect. So we know that the accelerating observers in the inertial vacuum, they basically see a temperature proportional to the magnitude of the acceleration. That's the only effect. So I'll basically exploit this correspondence and first work out things in the Rindler space. And then I would talk about what happens in the black hole case. So this is the picture in the Rindler case. So this is the BMS type shock wave, which basically passes through the Rindler horizon. Here again, the stitching is similar to what we did in the Schwarzschild case. So you have the Rindler spacetime, and it is stitched with another copy of the Rindler spacetime, which is acted upon by that symmetry. And hence you generate this particular BMS type shock wave. So the metric is denoted over here. Again, H is the Heaviside step function. So the metric is written again in Bondi type coordinates. And this is the BMS type supertranslation vector for the Rindler horizon. Now here, since the horizon is basically planar, we have this function, which is a function of the transverse coordinates, X and Y. And it basically captures the aplanar symmetry of the wave. So just like in the Schwarzschild case, here we have BMS shock wave, which is not, which has basically aplanar symmetry, and it has a energy momentum tensor, which is similar to what we saw in the Schwarzschild case. Now, the question that we would like to ask is, if you have this congruence of uniformly accelerated observers, once the shock wave basically passes, what happens to this congruence? What is the effect of this wave? Now, to answer this, we need to first understand what do we mean by Rindler trajectories in the third spacetime. So just saying that we want uniform acceleration is not sufficient to get a complete solution, because it only fixes the magnitude of the acceleration, but the direction is basically free to lie on, let's say, the sphere S2, which is orthogonal to the 4 velocity vector. So we must also have another definition. Now, Rindler trajectories in flat spacetime have this additional property that they are also basically planar. So if we have this, covariant definition of what we mean by a planar trajectory in a curved spacetime, then we could perhaps have a generalization of what we mean by Rindler trajectories. We are specifically interested in only in Rindler trajectories because these are the ones which detect thermal radiation in the background inertial vacuum. So what we essentially would need is a covariant definition, in which if we go to any event on the trajectory and construct a local inertial frame, then in that local inertial frame, your Rindler trajectory should look like a hyperbolic trajectory, like the way which you get in the usual flat spacetime. So that is the motivation. So the definition that we use is basically the Letov-Frenet equations in the curved spacetime. So these are essentially the generalizations of the Frenet-Serret equations, which we study in differential geometry, where you have a curve in Euclidean, three-dimensional Euclidean space, and that is described by scalar quantities like the curvature scalar and the torsion. And there you have 3 unit vectors to basically describe the tetrad, not the tetrad, basically the 3 normal orthonormal unit vectors. So the tangent vector, the normal, and the binormal. So we basically generalize it to the curved spacetime. So here you would have 3 scalars: the curvature scalar, the torsion scalar, and also the hypertorsion scalar. And here you would have now 4 basis vectors which would form that particular tetrad. And we generalize the Frenet-Serret equations by imposing how the unit vectors basically they evolve once you move along the trajectory through this particular matrix, which is defined over here. And once you have this particular definition, then defining a planar trajectory becomes simple. We just impose the condition that the torsion and hypertorsion is basically 0. So that guarantees that your trajectory is essentially planar. And saying this curvature scalar is a constant basically fixes the magnitude of the acceleration to be constant. So if you impose these conditions, you would find that it basically reduces to the usual definition of Rindler trajectories in the flat spacetime. And it also allows us to have a correspondence that if you construct a local inertial frame on any event on that trajectory, it will look locally hyperbolic. So in short, the condition basically reduces to this particular equation which I have shown over here. So here the 4 vector W is essentially the change in the acceleration vector as you move along the trajectory, and that vector W should be essentially equal to the unit velocity vector, and proportionality constant is the mod acceleration scale. So if you have this condition, then you would essentially have the required trajectory with torsion and hypertorsion to be 0. So if you impose this condition for the trajectories through the BMS shock wave, now note that on the shock wave you have non-zero energy momentum tensor and also non-zero curvature tensor. So essentially your space-time is curved on the shock wave. So you would need to have this condition to basically extend the congruence of uniformly accelerated trajectories across the BMS shock. So this is the solution. So essentially you start with that congruence of accelerated observers, impose the condition which I told you, and I'll tell you the result directly. So what we get is after the trajectories have passed through the shock wave, what happens is before the shock wave, the congruence of trajectories are orbits of the same boost killing vector. But after the wave has passed, each orbit is also an orbit of a boost killing vector, but that killing vector is different for different trajectories. And it essentially depends on where a particular trajectory has crossed that BMS shock. So the corresponding kick that the trajectory gets is basically described by the Lorentz boost matrix, which I have shown over here, which is dependent on that aplanar function which I mentioned earlier, which is a function of that transverse coordinates. So this is how essentially the classical part of the gravitational memory manifests for the uniformly accelerated observers. So you have this congruence, which basically passes through the VMS shock wave, and then each trajectory gets a different kick depending on where it crosses the wave. So retaining a memory of the shock wave. So you need to look at the congruence to basically talk about the classical part of the memory. Okay. So having talked about the classical part, now let me move to the quantum part. So for the quantum part, I would be basically putting massless scalar fields in this particular background. So I would be talking particularly about the entanglement between the left and right modes in the left and right Rindler wedge. So just as a notional thing, I have shown here two particular modes. So let's say the colored modes A and B correspond to one particular, let's say some K1 mode, and the blue particles over here correspond to some K2 modes. So these lie in the left and right Rindler wedge. The question we would like to ask is what happens when this basic shock wave passes? So you would need to solve basically the field solutions both before the wave and after the wave. And then using an appropriate stitching condition, you should basically try to evolve what happens to the positive frequency modes and the negative frequency modes after they pass through the wave. Now, since the shock wave lies purely in this right Rindler wedge, which we are basically interested in, the left modes are, they remain unaffected, whereas the right modes, they would evolve as per what the configuration of the shock wave is. So this is the basic setup. This is basically the Minkowski vacuum written in terms of the left and right modes. So we would be basically solving the field solutions before the wave, which is given in terms of the usual modified Bessel functions. And after the waves, you can write again the solutions using the super translation vector, and then writing down the appropriate matching conditions. What we find is basically the positive frequency modes and the negative frequency modes, they basically get mixed for the right part of the wave. So you have both non-trivial Bogoliubov coefficients, alphas and betas, the mode mixing coefficients and the particle creation coefficients. So I have just shown here the expressions, but what is the meaningful features that we can extract from that particular expression? So that is what I'm going to describe now. So we want to understand how does the entanglement change. Okay. So so we will have a measure of what the entanglement is before the wave, and then we will look at the same measure after the wave. Okay. So we basically look at, let's say, two modes first, and let's say the state is written in this particular form. So this is, let's say, some particular mode, and this is the second mode. And over here, the A and B correspond to the left and right modes, which I showed in the picture. And similarly, C and D are the other left and right modes, which I showed in the picture. And the measure, entanglement monotone measure, which we basically use to quantify the entanglement, is the negativity, because it's simple basically to work with it. Using the entanglement entropy becomes quite tedious, because like I showed you, because since you have mode mixing and particle creation, the reduced density matrix, once you trace out the left modes, it becomes highly off diagonal. So computing the logarithmic using the image trick or etc., it becomes too much complicated. So we basically use the relatively simple monotone of negativity. So this is basically the negativity before the wave. So before the wave, we know that for a single mode, only the left and right corresponding to that same mode are entangled. So A and B are entangled, and C and D are entangled. Whereas there is no entanglement between the cross pairs. Okay, and then we compute what happens to the entanglement after the wave has passed. So basically, you need to write down the vacuum states before the wave and after the wave. So since we have non-trivial betas, we know that the vacuum state before the wave for the right Rindler is not same as the vacuum state after the wave. So basically you have particle creation over here. So you use that to write the different creation and annihilation operators by using the standard basic relations. So I'll just tell you what the final result is which we get. So this is the table before the wave. So you have entanglement only between, let's say, A and B, and no entanglement between, let's say, B and D on the same side for two different modes. And of course, there is no cross entanglement between different modes on the left and right. But after the wave has passed, we find that the entanglement between A and B, it gets degraded to order lambda squared, whereas the entanglement between B and D, which was non-existent before the wave, it gets generated to order lambda. So all our calculations, they are basically in linear order in some perturbation parameter lambda, whose exact definition we don't need right now. And along with this,
you have 3 minutes.
Yeah, I'll just finish in 2-3 minutes. I'm just done. So yeah, along with this entanglement generation, there is also cross entanglement generation between C and D, but that generation is of order lambda squared. So the main entanglement generation which we see is between the two different modes on the same slide. So this is the main part of our result. So one could ask what happens to the quantum monogamy relation, which basically says that suppose if A and B are maximally related, then there is a restriction on the amount of entanglement that B can have with some other particular particle. So what we have checked is that for the entanglement monotone of negativity, since it follows this particular monogamy relation in terms of the squares, even though the degradation happens at order lambda square and the generation happens at order lambda, because you have the squares which occur in the quantum monogamy relation, it is basically safe. So there is no violation about it. So if you look at the now similar picture in the case of the Hawking radiation in the Schwarzschild geometry, what we see is initially we don't have any correlation in the outgoing, let's say, two Hawking particles, but once the BMS type shock wave, once it goes in, there is a linear order generation between the two outgoing Hawking pairs, whereas there is this degradation between the one of the particle of the pair which has basically fallen. So at least it goes in the way that we had hoped. But of course, this is only a perturbative computation. One would like to understand what happens at higher orders as well. Okay, so another part where our results could be applied is in this scenario. So if you have, let's say, just flat space-time and let's say two cavities, and the two cavities are at rest, and if you have some initial entanglement between them, and then let's say you make one of the cavity to move, to accelerate, and then again bring it to rest along with the first cavity, and then ask the question what happens to the entanglement between them, whether it basically redistributes, then our computation would also apply in this particular scenario, and one would have interesting results in this way. So I'll just mention this quite briefly. And one would like to have a particular general expressions in terms of, let's say, the local frames. So if you, let's say, have a general curved space-time, then we have seen that there are two ways in which the entanglement changes. One is due to the presence of the background curvature, and the other is due to the explicit motion. So in general, if you have some cavity moving in a curved space-time, the entanglement could change because of the combination of these two effects, and one would like to basically write them in terms of the local curvature invariants as well as the accelerations, etc. So that is the broad purpose. Okay, so with this, I'll just flash the summary. So I have talked about the BMS type symmetries and its connection with the memory effect. And I talked about a physical process version in which you can basically implant this super translation hair on a horizon by using this infalling BMS type shock waves. And then we investigated the classical memory effect for the congruence of uniformly accelerated observers. And then we saw that it basically gives a kick, and that kick is dependent on that planar inhomogeneity of the wave, and it records the memory. And in addition to the classical memory, once you talk about the background fields, then you also have this redistribution of entanglement because of that BMS shock wave, and that basically constitutes the quantum version of the gravitational. So I'll stop here and accept questions.
Okay, thank you. Now your talk is open for questions.
Thank you. So I can see Indranil has raised his hand.
Please ask questions.
Yeah, hi. So my question is regarding the shockwave profile that you talked about, the matrix shockwave. So how do you a priori choose the shockwave profile so that you get the memory effect? That is my question. Any shockwave profile would do it, or?
No. So the main ingredient is this BMS super translation vector. So once you know this particular diffeomorphism vector, which retains that asymptotic symmetry, then you use it to basically act it on a metric, and then you stitch the metrics together. So that essentially constructs your BMS type wave. So it's not any arbitrary wave that we have considered. It has to do particular with the type of the super translation vector, which is mentioned over here. So that defines the profile of the shock wave.
Okay, so C is here the super translation field, I guess.
Yeah, so that basically records the non-spherical geometry of the shock wave.
Okay, okay, okay. Thanks.
So no more questions. So thank you very much for all speakers and all listeners, all audience. Now our official problem is closed, finished, but you can use probably during 10 minutes, when in 10 minutes we will be off. Using this time you can discuss some questions. So people who are not going to discuss can switch off, and people who are going to discuss may do it now. Any questions, not exactly related to our talks today?